Hello everyone, and welcome back to this lecture series on BSP 303, that is Digital Systems and Applications. So we'll continue our discussion on the universal gates. So today I will discuss about the not or, that is NOR universal gate, and then if time permits, we will also try to see the arithmetic logic gates. Okay, so let us start our discussion and let us begin our discussion with the NOR gate, which I mean the basic of NOR gate I have already taught you in the last lecture. We'll continue right from there. So I'm sharing the screen. All right, so this is the you can see here on the screen that this is the 8th lecture of this lecture on this course. So we will continue our discussion on the NOR gate first. The basic of NOR gate I have already discussed in the last lecture. So let me just write down here again. Let me just revise it. Let me just write down the Boolean expression NOR gate. So we know that the Boolean expression for the NOR gate is A or B the whole complement. Or we know the symbol of NOR gate. The symbol. Let me just try to draw the symbol here. You will just have to draw an OR gate and then put a bubble at the output. This represents your NOR gate. Suppose you have the two input A and B and the output as Y. And this is the Boolean expression, the Boolean equation for the NOR gate. Okay. And we have seen that in the NOR gate, in the last section, that the output will be high only when both the input are 0. 0 or 0, you will get 0 and 0 complement is 1. If any one of the input is 1, then the output is, if any one of the input is 1, then the output is low. Okay, so the output, for the output to be high, both the inputs should be low, then only the output will be high. Okay, now before I go to the to the detail, or I can go to the, before I go to the implementation of basic gate using this NOR gate, I will show you the switching analog for this NOR gate. All right, so here let me show the switching analog for this NOR gate. I have a cell here, then this cell is connected through this to the output. Let us say this is the output. I have the output here. Okay. Now where would I put the switch A and B? So the two switches would be connected in parallel in this way. So let me just, so one switch would be here and another switch would be here. Okay. So let me call this as A and let me call this as B. So I would connect these two switches in this way here. So this is how our connection looks like. So this is my switch A and here I have the switch B, and let me call this as the output Y. Now the output will glow. You see from this, we have already been discussing such kind of switching circuits before also, but anyway, let me repeat. Now when these both are 0, 0 means they are open. You see current cannot flow through this path, and here also current cannot flow. So what happens when both of these are 0? What happens? Current will now flow through this to the load and then back to the circuit. So current, it will complete the circuit. That means the light will glow. When both the input are 0, 0, current cannot flow through this. That means the output will be high. Okay, now when any one of them is 1, let us say when A is 1, any one of them is 1. In that case, what happens? Current will come here. It will have two paths to go. One is along this one, which is having the higher resistance. Of course, there would be some load here, there would be some resistance. And one is this path. You see now the path through A, which is having no resistance. Okay, so of course the current will be flowing through this path. less resistance path, and then it will complete the circuit like this. So in that case, the bulb will not glow. Same thing will happen when B will be closed. So when both A and B are closed, current will be easily flowing through these switches, and it will complete the circuit, and hence it will not be contributed to the output. So when any one of them is 1, the output is 0. When both of them is 0, then only the output is high. That means in this case, the bulb will glow. So this is the switching circuit for a NOR gate. Okay, not forget. So let us now see the implementation of basic gates using this, the NOR gate. We will first start the implementation of using a NOR gate. Okay, so let me just go slightly down. Fine. So the first one is that I am just trying to build a NOR gate using a NOR gate. Okay, I am designing a NOR gate using a NOR gate. So what would I do? I would just build a NOR gate here, okay, like this, and then again, just like the previous case, I will connect the two inputs together in this way. I will give the same input, and then we'll see the output here. Let us see whether output is the complement of this input or not. Suppose I'm giving the input A here. Okay, let us try to verify this. So A means here also I will have A, and here also I will have A. And what is the operation of NOR? Operation of NOR is nothing but it would be A plus A the whole complement. It would be nothing but A plus A the whole complement. A or A the whole complement. Okay. Now A or A is A because we have 1 or 1 is nothing but 1. 0 or 0 is 0. Similarly, A or A is A. So I am getting A complement. So I'm giving A at the input, and at the output I'm getting A complement. That means this circuit is functioning like your NOT gate. Okay, if you give any variable at the input, you will get the complement of that variable at the output. So in this way, you can design the NOT gate using NOR gate. Okay, so let me go to the next one. So let us see the designing of OR gate using NOR gate. So the second one is OR gate. Okay, using NOR gate. Fine. So okay, so we need two NOR gate here. First NOR gate I am drawing it. Okay, and then after this I will be having another NOR gate connected in this way, and here I will give two inputs, which is to be given A and B, and here I will obtain the output. Okay, now this circuit will work as the OR gate because you give A and B at the output, at the input, you will get the output is equal to A or B. Let us see whether that is true or not, whether we are getting A or B at the output. Now you know that this is the NOR gate. The output here, it would be the output of this first NOR gate in this point. The output is nothing but it is A or B is the whole complement. Okay. Now this itself is working as a NOT gate. That means whatever I am giving at the input, it will be the complement of that input. Now this is my input ka complement. That means I am getting here A or B the whole complement. This is the input, the complement of the input. That means double complement. Now you know that double complement means the same variable. That means A or B, isn't it? By using De Morgan's theorem, or this is the rule that the double complement of any variable is the variable itself. Okay? Or you can even break this using De Morgan's law also. We'll talk about De Morgan's law, but here you see that you are giving A and B as the input, and you are getting A or B as the output. Okay, that means this is functioning as our OR gate. Now let me go and tell you about the last one, that is how we can design an AND gate using a NOR gate. Okay, so here I need three NOR gate. The output from here and the output from the other I will again fed as the input to another NOR gate here. This is another NOR gate. Okay. Then here the first NOR gate, it is functioning as the actually NOT gate here. I'm giving as if I'm giving only a single input. If I'm giving a single input to the NOR gate, then this will function as the NOT gate, isn't it? Just now we have seen. So what would be the output of this? This is a NOT, it is functioning as a NOT gate. So let us verify whether the output is A and B or not. So in fact, we can choose different color here. So the output of this one would be nothing but A complement, and the output of this one is, sorry, it should be your B complement. B complement. Now A complement, B complement is the input to this NOR gate. So the output would be, it is nothing but A complement or B complement, the whole complement, because this is the NOR gate, isn't it? Now A complement plus B complement, the whole complement. Now if you demorganize this, if you use the De Morgan's theorem, now this expression is nothing but it is equivalent to A and B, like the one which I have used in the last lecture. I have used De Morgan's theorem to break this. So you can do that. I mean, okay, let me just show you how this is actually equal to A and B. Suppose from first step, what is the next one to demorganize? You have to remove the overall NOT sign. This is the overall NOT sign. You just remove, first you remove the overall NOT sign. Okay, fine. Then you change the AND to OR and OR to AND. That means you have to change this OR to AND. So the next step is you just need to change this OR to AND. Okay. And the next step is that recomplement the individual variable. Now this A complement and B complement are the individual variable. You will have to recomplement it. Okay, and B, one complement, double complement. Already one complement is there. So A double complement is nothing but A, and B double complement is nothing but B. So in this way, I am just getting this A and B. That means this expression is nothing but it is A and B. Okay. So this circuit, whatever is seen here, it is working as the AND gate. So in this way, we can design an AND gate using a NOR gate. Okay. So let us proceed further. So this is about our universal gate. So, but before we go to the next type of logic gate, that is the arithmetic logic gate, let me tell you how we can construct this NOR gate using a transistor. Okay. We know that according to the truth table, we know that the output is high only when both the input are 0, isn't it? So we'll try to see that. I'm going to the next page. So the discussion would be, I'm just going to design a transistor NOR gate. Okay. Let us see how we can design this transistor NOR gate. We require just 2 transistors here. So I'm having one transistor here and the other one here. These are again NPN transistor I am taking. Okay. So this is also an NPN transistor. You can see from the symbol itself. So what I will do, I will take the collector of these 2 and combine together here. Okay. And I will give the potential at this point, that is plus 5 volt potential, and through this one I will obtain the output. Let us say this output Y I am obtaining from here. Okay. Now the input, you will give it one input here A and the other input here B. This I will call this as A. Okay. So I will join the emitter of this 2 and then make it ground connection here. Okay. So when both A and B are 0, 0, then you will get a 0 at the output. Let us verify this. When A is 0 and B is also 0, that means what happens when A is 0, the transistor will not work. Similarly, this transistor will also not work. Okay. So the current cannot flow through these transistors. Both these transistors. That means what happens? Whatever is the potential here, all this potential, since the current cannot flow through this to the ground, all of this potential, this is, let me call this as R, all this potential will be appearing across this point N. Okay, this point N will also be driven to positive potential, and since current cannot flow through this transistor, all the potential will be appearing across this Y, which is the output. That is, Y would be at a very high positive potential, that is plus 5 volt. Okay, that means Y is equal to 1. So when both the input are 0 0, output is 1. Now when any one of the input is 0, or any one of the input is 1, when any one of the input is 1, then the output, or both is 1, then the output is 0. Okay, let me verify this. Let us say that let us say that A is 1 and B is 0. Okay, so now I'm giving 0 to this transistor, so this transistor will not work. We already know this, isn't it? This transistor, because for this transistor to work, you need to apply some positive potential, because this is an NPN transistor. And now you see here I'm giving a logic 1 here. That means I'm giving some positive potential here to the base of this transistor, so the transistor will start working. Now when the transistor work, what happens? Current will be flowing through this transistor to the ground, like this. Current will be completing the circuit. Okay, as if this is the plus terminal and as if this is the negative terminal. Current start from plus terminal and it ended towards the negative, so the circuit is completed. Now in this case, what happens? Since the current is flowing through this, let us say this is R, all the voltage would be dropped across R and nothing would be appearing across this point N, because the current is flowing through one path. So the point N will be driven to 0 potential. And since the point is driven to 0 potential, the output would be at logic 0. That means 0 volt. Okay, so in this way, when any one of the transistor out of these two is working, or when both the transistor are working, then you will get a 0 at the output. Otherwise, when both are 0, input are 0, then you will get a high at the output. Okay, so this is about your NOR. This is about your transistor NOR gate. Okay, we will now go to the you can just, there are many questions. There can be many different type of questions on this NOR gate. You have to remember the switching, the switching circuit for this NOR gate also. Sometimes these switching circuits, this type of questions are also asked in different type of competitive exams also. Okay, they will give you some of the switches and then they will ask you like what would be the output of that switch output expression. So we'll try to see some questions, but before that I will just try to begin this arithmetic circuit gate. Okay, so the next topic of discussion would be arithmetic circuit gate. Arithmetic gate, I'm just writing arithmetic gate. Okay, so universal gate we have just finished discussing, so we'll now discuss the arithmetic logic gate. So what are the two type of arithmetic logic gate? There are two type of arithmetic logic gate. One is this XOR gate. This XOR gate is known as the exclusive OR gate. Okay, and then another one is, the next one is XNOR gate. So this is nothing but this is exclusive not OR gate. That means exclusive NOR gate. XNOR, in short, it is not called as XNOR, and the other one is exclusive OR. Okay, why they are known as arithmetic gate? Because most of the arithmetic circuit they utilizes this XOR gate and XNOR operation actually. Okay, so that is why they are known as arithmetic gate, because different type of arithmetic circuits they utilizes, most of the time they utilizes these two popular gates, and that is why they are put under this category of arithmetic circuit gates. Okay, so without any delay, so let me just start the first one, that is XOR gate. So this XOR gate is known as the exclusive OR gate. Okay, so first I will just try to draw the symbol. I will first draw the OR gate. Okay, Then there will be a line in this way, OR gate with an input line in this way. It is known as the exclusive OR gate. Okay, so let us say y is the output, and the operation, the Boolean expression for y is a. This symbol now, this symbol will tell you that it is exclusive or simple. Okay, a exclusive or b. So what is the exact Boolean symbol for this one is that it is nothing but a. It is nothing but it is a complement b plus, or you will have ab complement. Okay, a complement b or ab complement. So this is nothing but this is exclusive OR gate. Okay, now based on this one, see, it will be very easy for you to write down the truth table, isn't it? In the truth table, you need to write down the true input and the value of the output. Okay, so we can easily, based on this equation, Boolean equation, we can easily write down the output. And if we see this Boolean equation carefully, if we see this Boolean equation output carefully, we can conclude from here that the output is 1 if it's either input but not both is 1. Okay, if any one of the input is 1, then the output is high, otherwise the output is 0. Okay, so if any one of the input is 1, then only the output is 1, otherwise it is 0. Okay, so if I have to, I mean, draw the truth table for exclusive OR gate, this is the truth table for OR gate. Okay, so I will write all the possible combination of A and B. Now the output is high only when any one of the input is high. Okay, so you see only the second and the third case you have the any one of the input high, then only the output will be high, otherwise the output would be 0. So the output is 0 when both the input are same. You can also say that the output is 0 only when the input are same. Same input means output would be 0, whether it is 0 0 or 1 1. I mean, you can always verify this with the help of this expression. Okay, so I am not doing here, so it is not that much, I mean, difficult. You can verify this yourself. Like y, I have already told you that it is a complement b plus a b complement. You just put the value of a and b for each case here. You will obtain this output. Okay, so same input means output would be 0. Same, you see here. Here also we have 0 0, so output is 0. Here also we have 1 1, so the output is also 0. So same input condition will give you the output to be 0 output. Okay, now the output is high only when any one of the input is high, then only the output is high. Okay, fine. So all right, so we can come to some of the very important I mean conclusion from here before we actually go to the next type of arithmetic gate. That the first one important conclusion from here is that, okay, if any one of the input is 1, then the output is complement of another input. So if any one of the input is 1, then the output is complement of another input. For example, in this case, okay, so let me give this as here. Okay, and I will give the input, another input b is equal to 1. Now if any one of the input is 1, then the output is complement of another input. So if any one of the input is 1, then the output is complement of another input. That means y should be the complement of another input. How? You can check it by yourself. So just apply the exclusive OR operation here. You know that y is equal to a complement b plus a b complement, isn't it? So now what is a? A complement you can just keep as it is. What is b? B is 1, or you have a b complement, because since b is 1, 1 complement would be 0. Okay, fine. So a complement into 1, you have this a complement plus a into a and 0, you would get 0. Now a complement or 0, you would just get this to be a complement. Okay, so you see, if any one of the input is 1, the output is complement of another input. This is one important conclusion from here. Okay, so the next one, let me tell you the next important. Now if any one of the input is 0, the output is another input. Okay, For example, I am again drawing an exclusive OR gate. Another important conclusion is that if any one of the input is 0, let us say I'm giving this input B equal to 0. Okay. If any one of the input is 0, then the output is another input. What is another input here? That is A. Okay. You can verify this. In this case, A complement B plus you have A, B complement. Now, A complement and 0, or you have A, B complement. Now, B is 0, so 0 complement is always 1. Okay, so this part you will get 0 and this part you will just get A. So the answer would be A. Okay, so two important conclusions we got from exclusive OR gate. The first one is if any one of the input is 1, which I'm showing now in the screen, the output is the complement of another input. And the second one is that if any one of the input is 0, the output is another input, that is A in this particular case. Okay, so these are some of the very important conclusion which we can draw from this exclusive OR gate. Okay, so today we will just stop here, and in the next lecture I will try to cover, I would try to cover some of the topics on extra topic on this. One more gate we have to discuss, that is the XOR gate. Okay, we'll try to see XOR gate, and in one lecture I will try to discuss XOR gate as well as some of the important questions if possible regarding this exclusive NOR gate. Okay, so I'm just stop sharing the screen. So thank you everyone for attending this lecture. So in the next class we will again see some of the more discussion on this logic gate. We are still not yet done with the logic gate. We have few more important points to discuss in the logic gate, and maybe I would try to give you some of the questions also in the next lecture related to this logic gate, whatever we have done till now. So thank you everyone for joining.